Hello everyone. This is engineer Sadaqatali, and you are watching my YouTube channel, Real Time Simulation World. So, in today's video, I am going to discuss with you about MMC based AC-DC rectifier, which is developed using full bridge submodules. So it was seen that there is no proper, simulation of how you can utilize MMC as a rectifier. Mostly people do work or simulation related to MMC as an inverter. So in today's presentation, I'm going to discuss with you that how you can basically simulate full bridge based MMC for AC-DC conversion, right? So in today's video, I'm also going to show you that how it can be simulated in MATLAB Simulink. Alright, so this is my agenda. I'll be discussing about briefly about MMC and its architecture as a full bridge submodules, full bridge versus off bridge submodules. I will walk over the Simulink, model. I will discuss briefly about the control strategy, the modulation and switching strategy. I will show you the results and some applications, and in the end conclusion. So you all know that what is HVDC. So HVDC is a high voltage direct current transmission line that uses DC power to transmit electrical power over long distances. So why HVDC is preferred? Because at longer distances it gives us more stability and less losses compared to AC transmission line. So in HVDC, the latest topology is the modular multi-level converter, which is a voltage source converter topology, which is developed using discrete submodules. Those submodules can be half bridge and full bridge. So the half bridge submodule is basically the one which contains only two switches and a capacitor connected across them. Whereas the full bridge submodules, in full bridge submodule we have four different switches and capacitor is connected in between them in such a way that it can generate positive voltage, zero voltage and negative voltage, whereas the half bridge submodule can only generate positive voltage and zero voltage. There is no reversal of voltage due to less number of switches in half bridge submodule. So this is our full bridge submodule where we have four different switches and a parallel diode is connected there. So we have four different switches and they are operated in such a way that if S1 is on and S4 is on, both S2 and S3 are off, you will get positive voltage. Similarly, if S2 is on, so the current direction will be this way, the opposite to the previous one, and similarly you need to turn on the S3. So both S1 and S4 will be off for the negative voltage section. And for the zero voltage generation, you need to turn on either S1 or S3 or S2 or S4. So for the zero voltage you have two possibilities, and for the positive and negative voltage you have only one possibility, right? So majorly the full bridge submodule is used due to the DC fault blocking capability in HVDC system, right? So we can compare both half bridge and full bridge submodules. Like as I told you that there are two switches and a capacitor, no DC fault blocking capability, like that whenever the fault occurs all the switches are turned off, right? So there is no possibility of DC fault blocking, whereas in full bridge we have DC fault blocking capability. Losses are less because the number of switches are less, and losses are higher in full bridge submodule. Cost is also less, whereas the cost in full bridge is twice due to the more number of switches. Power flow in half bridge submodule is unidirectional, whereas in full bridge you have a bidirectional. Black start capability in half bridge is not supported, where in full bridge it is supported. Right, voltage levels, we have n+1 levels if you are using it as a inverter, and you have two n+1 levels if you are using the full bridge as an inverter, right? So this is a typical module, the model that we have, right? So here basically a grid is connected, then there is a transformer, and after that transformer we have a we have some RL, you know, inductance of the line, and then we have a MMC, full bridge based MMC, and then finally you can see here that there is a load connected. Okay, so I can show you the Simulink model. So this is the Simulink model for this rectifier. So you can see here, right, the grid is connected, and after the grid there is a transformer, right, which steps down the voltage so that we can operate our uh, you know MMC, and there is a load connected. This is the load, right? So inside this you can see that basically the gate signals are coming. So there are a lot of signals because we have number of full bridge submodules. Each arm we have four full bridges connected, and there are 8 total full bridge submodules in complete single phase. So in each phase you can see there are 8 submodules, 4 in lower arm and 4 in upper arm, and we are basically measuring their voltages through this measurement block. So we are using a built-in full bridge submodule that is available in the Simulink, right? You can see there are 4 switches and a capacitor, right? So this gate signal needs basically 4 signals so that you can operate this full bridge. So there are 4 switches, right? So yeah, this is our circuit, and this is our control part, right? So in the control part we are controlling different things such as the DC voltage, DC current, circulating current, and we are taking the grid voltage and line current as a reference, right? We also have this module voltage balancing, uh, you know so this control I'll show you later on. So if I can run this, I can basically show you that how the outputs are coming. So basically currently you can see that the reference VDC reference is set as 3600, which is 3.6 kV. So 3.6 kV, all right. So you can see this is the DC voltage. So this DC voltage will settle down near around 3.6 kV, and this is the DC current which is flowing according to the load connected at the output. So you can basically see that it is trying to settle around near around 3.6 kV or something, right? We also have other parts such as the submodule voltage. So it is also, you know, somewhere around 1000 volts, right? We are also controlling the circulating current, We also have this control over here. uh, Over here. So basically this AC-DC controller will give us the reference voltages for the modulation signal. It will also give us the voltage that needs to be subtracted from this modulating signal, so that the circulating current is controlled, right? After that, there is a voltage balancing algorithm, right? So for the voltage balancing algorithm, we need how many submodules needs to be inserted. We need the uh, submodule voltages, need the arm current. So this is a full bridge submodule. So the basically the arm current can be positive and as well as negative. Now currently you can see that uh, the fault scenario is not added in this part because uh, that is the capability of the full bridge submodule, that whenever the fault occurs, so it blocks the DC fault. All right. So in the control part, this is our the roadmap. We have AC grid voltage measurements, voltages and currents. Then we are using the DQ transformation. We are transforming them into the DQ. Then we have a DC voltage outer loop, which is a VDREF, uh, which which was here. We stop this. It is currently running. So this is the VDC ref 3.6. We can increase this if you want up to a certain level. Let's say we make it 3 kV. So if you make it 3 kV, your reference now has changed. So you will get the output voltage near around 3 kV. Okay, let me minimize them. So now our voltage will be 3 kV. So let it settle down until then I can explain this part. So after that, the VDC ref basically generates the ID ref, and that ID ref goes in here, current inner current control loop, where we have the ID and IQ control. Then after this, we have reverse transformation, ABC and DQ. Also, the circulating current control is happening here. After that, we have NLC and gate signal generation. So this is the detailed discussion of each control, where we have DC voltage control loop, current control loop, circulating current control loop, and then modulation. These are the different states of the code. All right. So here we have explained that how basically the switching function is performed. So this is the reference signal that we have sent. This is the circulating current voltage reference that needs to be subtracted from the you know uh, the modulating signal in order to generate the different reference for the upper arm as well as for the lower arm, right? Then we have a level conversion and PWM quantization. Then after that we generate these output levels for the you know voltage balancing algorithm. Then we have a capacitor voltage balancing. We need to find how many submodules needs to be inserted. We need to check the current direction. Then if the arm current is greater than 0, it means we need to insert the low voltage submodules. and if the arm current is less than 0, we need to insert the high voltage submodules, right? So this basically balances your submodule voltage, right? So the output will be a signal that will go towards the switches. So this was the output that obtained. This is circulating current and submodule voltages. So this is basically the analysis that these were obtained. So let me show you now the voltage. You can see that it settles down near around 3.6 kV. So I can minimize this, and I can stop this, and let me zoom this. So you can see that this is 3 kV, right? So whatever the reference is, it will change it according to the that particular value, right? All right. Okay. So yeah, there are many applications such as offshore wind farm integration, VSC, HVDC interconnector. We have urban power and feed. We have multi-terminal HVDC grids. We have DC microgrids and other applications such as it is also being used in the railway traction as well. So the detailed modeling basically helps you to analyze each and everything. You can monitor these capacitor voltages, you can control them. uh, so yeah, and mostly people use it for the inertia support as well in the system where we don't have synchronous generators, so that the the stored energy in the capacitors can also be utilized in such applications, right? So yeah, this is all about this presentation. If you have any question, you can comment. uh, Thank you.